All right, welcome to The Explainer. Today, we are getting right into a seriously fascinating technical deep dive. We're unpacking the engineering architecture behind Contentstack Launch, specifically looking at how they built a custom rate limiting system they call, get this, the invisible shield. So if you've ever wondered how a massive platform protects its infrastructure from just a total flood of traffic at scale while staying completely unnoticed by normal, everyday users, well, you are absolutely in the right place.
Because honestly, this is the ultimate question for any hosting platform, right? How do you actually block an attack without slowing down legitimate users? Out on the open web, you really can't control who or what accesses your applications. You've got bots, automated scrapers, full-blown DDoS attacks, the works. The core engineering challenge we're exploring today is exactly how to stop that bad traffic dead in its tracks without adding even a single millisecond of latency for the real human users who are just trying to use the product.
So here's our game plan for today. First, we'll look at the need for a shield, then why CDNs fall short. After that, we'll break down the tiered token bucket algorithm, look at an unforeseen engineering problem they hit at scale, and finally, check out their ingenious post-allocation fix.
Okay, let's jump straight into part one, the need for a shield, focusing on isolation at scale.
Right, so first things first, we need a baseline. Contentstack's core philosophy here is pretty simple. One customer's massive traffic spike should literally never become another customer's problem. And to achieve that kind of strict resource isolation, robust rate limiting is absolutely mandatory. By controlling the exact volume of requests allowed in a specific time window, any excess traffic just gets gracefully rejected before it ever has the chance to tax the core infrastructure. It's basically the bouncer at the door making sure resource isolation actually works.
Which brings us to part two, why CDNs fall short, or what we can call the edge bottleneck.
Now you might be thinking, what's the most obvious place to put a rate limiter? At the edge, right? Usually right there at the content delivery network layer. CDNs sit in the direct path of every single request, and they are blisteringly fast. But here's the catch. A modern CDN operates through hundreds of independent points of presence spread all over the globe. And those independent nodes, they lack global coordination. This means a single organization could easily blow right past its intended global limit simply because each individual node is only counting its own local slice of the traffic.
So you end up with a real catch-22 for edge-based rate limiting. If you rely on those independent CDN nodes, well, you allow limit breaches because there's zero coordination. But if you force a global CDN coordinator to keep track of everything, you suddenly introduce a network round trip for every single request. And that adds massive, totally unacceptable latency into a layer that was literally designed to eliminate latency. So for accurate per-organizational enforcement that doesn't slow things down, the CDN just isn't quite smart enough on its own.
So, the engineering team had to dig a bit deeper. Let's explore Section 3, the tiered token bucket and finding the right algorithm.
When they started evaluating the classic rate-limiting strategies, they looked at a few options. The fixed window approach is super simple, but it has this fatal flaw where it allows double limit bursts right at the time boundaries. Not great. Then there's the sliding window log. Super accurate, sure, but it requires incredibly expensive storage at scale. So, that leaves us with the industry-standard token bucket. It's fantastic for handling traffic bursts and giving you really smooth limits. But it's notoriously complex to implement in a distributed system.
And honestly, that was it. The real challenge wasn't actually picking the token bucket algorithm itself. The absolute nightmare was figuring out where to store the bucket. Think about it. If you stick that bucket in a centralized database that all your servers have to share, then every single customer request triggers a database round trip. At true enterprise scale, that creates a massive bottleneck. It adds completely unacceptable latency right onto the critical path. Total non-starter.
So to get around this, Contentstack engineered a really clever two-tier architecture. Here's how it flows. When a request comes in, the server first checks a tiny, localized bucket held right there in its own memory. Fast, right? Now, if those local tokens happen to run out, only then does it reach out to the big global database to check total usage. It pulls down a fresh new batch of tokens, stores them locally, and instantly goes right back to serving requests from that local reserve.
And the performance impact of this specific design is just staggering. Roughly 95% of all requests hit that local memory fast path. That means zero, literally zero network calls to the database. The slow path, where it has to coordinate with the global database for a refill, that only happens about 5% of the time. They essentially built an architecture that successfully enforces global limits without sacrificing a drop of local speed.
But of course, as anyone in software engineering knows, deploying at scale always reveals some hidden surprises. Let's move on to Section 4, the unforeseen engineering problem, also known as the pre-allocation trap.
This quote right here captures a really harsh reality of infrastructure. In any distributed system, traffic is simply never perfectly balanced. Your load balancers are constantly routing requests dynamically. And what this does is it creates hot servers, or pods, that end up handling a massive, totally disproportionate share of the requests, while other servers go completely cold and just sit there idle.
Well, it turns out this imbalance completely broke their initial design. Originally, they were using this pre-allocation method. Basically, when a server received its very first request for a specific organization, it would instantly claim a full batch of 20 tokens from the global database right up front. Okay, so picture this. A server claims those 20 tokens, serves maybe just one single request, and then the load balancer decides to route all the rest of the traffic somewhere else. That server goes cold. So what happens to the other 19 tokens? They become what the team called stranded tokens. The capacity has technically been drained from the global database, but it's never actually going to be used by that cold pod. The consequence? The global database basically gets tricked. It thinks the organization has maxed out its plan, which starts causing false denials for the hot pods that are actually desperately trying to use that capacity. It's a total mess.
So, how do you fix a crazy systemic issue like stranded tokens? Let's dive into our final section, the post-allocation solution.
The engineering team came up with a brilliant little flip in their logic. Let's compare the two approaches. The old way, pre-allocation, claimed global tokens up front, creating that massive risk of stranding them on cold servers. But the new way, post-allocation, actually bypasses the database completely at first. It starts every bucket with a set number of tokens that live entirely in local memory. The servers can just begin serving requests instantly. It only deducts from the global database once those initial local tokens are completely exhausted.
And here is the absolute magic of this post-allocation setup. If a server goes cold before it exhausts its local tokens, the local time window just quietly expires. Those stranded tokens literally just evaporate locally, and the global counter is never even touched. This completely eliminates those false denials for the hot servers. Sure, you trade off a tiny bit of initial overallocation during unexpected bursts, but it ensures perfect fairness and true zero latency performance during normal, everyday operations.
So, let's summarize the ultimate benefits of this architecture. The Invisible Shield successfully globally enforces a customer-specific plan limit across the entire platform. It rejects DDoS traffic early, well before it can consume precious resources. It heavily prioritizes a zero-latency fast path for 95% of all requests. And, as a bonus, it adapts automatically to plan changes without requiring any redeployments. Basically, they completely achieve their goal, infrastructure-level rate limiting that is incredibly robust, yet stays 100% invisible to the customer. So I want to leave you with this thought to chew on. We've just seen how flipping one really simple logical step, moving from pre-allocation to post-allocation, solved a massive complex scaling issue. So how will you apply these distributed systems principles to balance global accuracy with zero-latency local execution in your next build? Because whether you're dealing with token buckets, progressive disclosure, or complex resource isolation, remember this: the absolute best infrastructure is the kind your users never even know is there. Thanks so much for joining me on this explainer, and keep building brilliant systems.